Welcome to MIG, a course taught at the University of South Florida. This tutorial is about using servo motors and analog inputs with the Arduino. We will discuss servo motor hardware, communication with servos, and the use of analog inputs. A servo is different from regular motors because it has a position sensor. It always knows where it is. This allows to position it precisely at a desired angle. The position sensor is usually a potentiometer. We see here in the figures the internal setup of this servo motor. On the outside here we have gears that connect the motor shaft to the actuator shaft, and the actuator shaft connects directly to the potentiometer. So as the motor turns the gears actually rotate not only the actuator but also the potentiometer. So by reading out the potentiometer, we can know at what position, at what angle the actuator is set. One of the drawbacks of this scenario is that potentiometers typically do not have a full 360-degree rotation, and so therefore most of the servo motors are able to turn only less than 180 degrees. Let's look into the control circuitry for servos real quick. If you're not electronically inclined, then you can just jump ahead the next two slides and go directly to the pulse width communication with servos. Here this circuit is a strictly analog circuit to control a servo. It's based on negative feedback, and so what we want to do is we want, with a control potentiometer, we want to control the position of the servo motor. And if you remember the previous slide, we have a potentiometer connected to the servo actuator, and so as the motor spins we actually are turning this potentiometer here. And so both potentiometers are connected between plus and minus 5 volts in this example. And so by setting the swiper of the potentiometer, we actually can generate a voltage that is between -5 and +5. And so we have that here at the actuator potentiometer, and we have the same at the control potentiometer. Okay, so as the motor sits at a certain position, this actuator potentiometer will output a certain voltage. And so this voltage is fed into the positive input of this differential amplifier, this op-amp, here called LF411. So the control potentiometer does the same thing, so we have a voltage here at the negative input. Okay, so this amplifier here, all it does is it compares the two inputs, the positive and the negative input, and it makes a voltage at the output here that is either positive if we have a positive difference here, or it is negative if we have a negative difference here. So if this potentiometer is higher than the control potentiometer, then we get a certain polarity here at the output, and if it is lower than the control potentiometer, we get the opposite polarity at the output. This voltage at the output of the op-amp then controls these two transistors that are in a push-pull configuration. If the potential is high, then this transistor opens up, and so a current would flow from 5 volts into ground through the motor. If we go low here, then this transistor opens up and we pull a current from ground into the -5 volt rail of this circuit. And so we get the current flowing in this direction or in this direction depending on the polarity. So this would change the rotation of the motor from forward to backwards, or well, depending on how it is connected. So depending on the motor polarity, we can set it up that we get a negative feedback loop going. So if the voltage is too high, then the motor will try to reduce the voltage and come to a rest. And that means that by turning this potentiometer, we can make the motor follow and try to set this actuator potentiometer to the same position like the control potentiometer. Now we fast forward into the microcontroller age, and essentially we can use the same circuit if we want to control the servo with a microcontroller, but it would not be convenient to use that control potentiometer that we had here, and so instead there is a control circuit integrated into the servo that can evaluate a pulse width modulated digital signal that the microcontroller can feed into it. And so this signal now, depending on the pulse width that we have here, can then output a control voltage that goes into this differential amplifier, and then the same thing happens. So here we go. This is how the Arduino communicates with a servo. Practically all servos use this communication protocol. And so the Arduino just puts out pulses at a 50 Hertz frequency. So every 20 milliseconds it makes a pulse. And the length of this pulse now, that defines the orientation of the servo actuator. And it seems that all servos follow the same convention, that we have 0.5 milliseconds pulse width corresponds to one end of the range of motion, and 2.5 milliseconds corresponds to the other end of the range of motion of the servo. So the servo that we have in the Arduino kit, that has about 160-degree range of motion. And so if you would feed it 0.5 milliseconds width, pulse width, then it would be on one end of its range of motion, and if you would feed in 2.5 milliseconds, then it would be 160 degrees in the opposite direction. And so any pulse width in between that you can achieve with the Arduino will allow you to set the actuator at a certain angle. Let's get real and see what the servo can do for us. This is my circuit as a fritzing schematic. Here is the servo. It is hooked up to the power rail, which I connected here to the Arduino 5 volts and ground pin. And then the control line for the servo, that goes here to digital pin 9. We also have a potentiometer connected, right? So here between 0 and 5 volts. And the swiper of the potentiometer, that is connected with the green jumper to the analog pin A0. So the goal of this setup is that I can control the servo by turning the potentiometer. So we're sort of simulating the analog setup that I just discussed, but we're doing it with the Arduino. So the analog signal here is converted into a pulse width signal that then comes out here at pin 9 and is fed into the servo. Here's the breadboarded setup. Here we have the servo, and the servo is connected. If you look real close, here you see the red and the black jumper. They go into the power rail, and here we have the control line, the orange wire that goes into pin 9. And this is the potentiometer. It's connected between 5 volts and 0 with two jumpers that are hardly visible, and then the swiper of the potentiometer goes into pin A0 on the Arduino board. Let's see what it does. So you see how the potentiometer directly defines the position of the servo. I hooked the servo control pin up to my oscilloscope. If you're new to oscilloscopes, what we see here is a time-resolved signal. So on the x-axis we have the time, and if you look down here, it's set to 5 milliseconds. So each of the squares here is just 5 milliseconds. So each of these pulses are just about 4 times 5, 20 milliseconds apart. So that's the 50 Hertz pulse signal. And now let's look at the y-axis. That is the voltage that is being applied, right? The Arduino puts out 5 volts, and here we have set it we set it to 2 volts per square. So this is just a little bit above 4, maybe 4.5, 4.7 volts that is going into the servo. on the control pin. So the width of these pulses now, that gives us the orientation of the servo. And in this experiment, like in the movie before, I just turn the potentiometer left, right, and we can observe now what happens to the pulse width. If you remember, the pulse width should go from about half a millisecond to 2.5 milliseconds. So let's see what happens. Right now I'm on one end, and now I turn the potentiometer back and back to the first position and back over. So now I'm changing the time base, so we have 500 microseconds, half a millisecond per, and you see nicely that we're moving about 2 milliseconds between the shortest pulse and the longest pulse. Now it is time to look at the Arduino code that made this experiment tick. So we start out with including the libraries, and actually this sketch is again a demonstration of the power of libraries. Just a few commands here and everything is working. So we include the servo library. This is an Arduino standard library. I said before, most servos behave very similarly, so this is a library that you can use for pretty much any servo that you buy. Then we define the pin where we hook up the servo. Right? We started doing this not using numbers in the code, but using the define pre-compile directive in order to create a better readable code. We do the same with the potentiometer pin. That is 0 because it's hooked up at A0. And so the next command here is to instantiate a servo, and we call it my servo. Apparently this library can do a maximum of 8 servo objects, so you could hook up 8 servos to the Arduino. However, if you did that, you need to keep in mind that motors draw a lot of current, especially if they're under load. And so I would not recommend to run more than one servo on the Arduino directly from the USB bus. So if you use more, then you should hook them up separately with a power supply. Okay, here on to the setup function. Here we have a serial begin, so we start a serial communication at 9600 baud. This is just if you want to see down here what the servo position is. Then we use the attach method of the servo. Here basically what we do is we tell the object on what pin it is running. So the servo pin number 9 is entered here by the compiler. And then we have a very short main loop. Here we define a temporary variable, local variable, and we set it to 0. Then we use this variable and we use the analog read command. So this analog read command essentially gets the voltage from the analog input pin in a 0 to 1023 range format. Right, we have 10 bits in the digital analog converter, and so the 0 to 5 volt range is projected onto the 0 to 1023 range. So if the potentiometer is about in its middle position, then we would get about 512 or so as a readout through the analog read command. So this value is stored in value. And now we use the servo method write on our myServo object, and we now tell the servo to what angle to go. So the write method has as input the angle where you want the servo, and it assumes that the servo goes from 0 to 180. However, you need to keep in mind that servos rarely really do a 180 degree sweep. So you need to actually test your servo and figure out what its sweep is, and then actually scale the 0 to 180 range. So we're using a new command here. It's called map. That is in the Arduino commands. And essentially what it does is it takes a value, right, our value here, then we tell this map function what is the range of this value, and then we can tell it what is the range this range should be mapped onto, right? Because write wants a 0 to 180 degree input, yet value comes from 0 to 1023. This is a very convenient function because we can very easily project the 0 to 1020 range onto the 0 to 180 range, and then the servo can understand this value. Okay, and this here simply drives the servo to the right position. That's all you have to do. It's a very powerful method. Okay, then we have the serial print command, and if we would start the serial monitor, then we would actually see that the value is changing as we turn the potentiometer. Right, so in the loop, all that happens now is we read the potentiometer pin and we drive the servo to the location. Then we print the value and we go back and read the potentiometer pin. So very elegant, just by using libraries and powerful Arduino commands. We have a very short loop here that allows us to map a potentiometer onto the servo position. Let's have a look at the servo library. Remember, it's always good to have a look at the header file, because the header file will tell you immediately what methods are available. So I'm switching now to Xcode, where I opened the servo header, and so this is actually a very nicely commented library. Here we have some this description of the methods, right? So we don't even have to go down there to the header. It's down here. Here you have all the definitions of the methods, but it's much better to look up here. So the attach you just saw, we used attaches a servo motor to pin. Here you can actually expand the attach command. You could actually tell min max is the microseconds that define the range, right? So if you would have a strange servo that would have not a full sweep in terms of pulse width, then you could enter different values here. Right, we just used that. That puts the servo at the right at an angle. We also have right microseconds. Here you could actually enter the microseconds that you would want in the pulse width, and then it would directly do that. This may be more precise if you have a data sheet for a particular servo. Then there's the read command. We use that for the serial print. Right here you can actually read out the position where the servo is located. And you can also get that position in microseconds. Here you can actually see if a servo is present, and you can also detach a servo, so this pin is liberated after you use this command. In case you were wondering about the Arduino analog input pins, here's a quick description. We have 6 analog inputs. They're on the Arduino board. Here you see it, analog in, and they're labeled A0 to A5. These inputs are connected to an analog digital converter, or ADC in short, that is on the Atmega chip. And these pins, they can read voltages from 0 to 5 volts, and they give a range of 0 to 1023 back, so that if you do the math, that gives you a resolution of 4.9 millivolts, and this 0 to 1023 value you can get through the analog read function. There's one thing to note, since there's only one ADC on the Atmega chip, you can really only read one pin at a time, and these pins, they are basically multiplexed onto that ADC one at a time. This concludes our tutorial using servo motors and analog inputs with the Arduino. Thanks for watching.